The tetravalence of carbon can be explained from its valence shell electronic configuration. We know that the outermost shell of an atom is known as the valence shell. Electrons present in the valence shell, that is, valence electrons, take part in the chemical reaction. The electronic configuration of carbon is 1s2, 2s2, 2px1 and 2py1. This means that the valence shell has only 4 electrons. All elements tend to complete octet in their valence shell to become stable. Since carbon has 4 electrons in its valence shell, to complete its octet, the valence electrons of it form 4 covalent bonds with atoms of other elements. This characteristic of carbon atom, by virtue of which it forms 4 covalent bonds, is called as tetravalence of carbon. Thus, carbon forms a wide range of compounds. In this example, methane is formed by sharing 4 electrons of carbon with 4 hydrogen atoms. The formation of molecules and their shapes can be explained by considering the hybridization of s and p orbitals respectively. Now, let's look at how hybridization explains the shape of ethene molecule, that is, C2H4. In ethene, each carbon atom undergoes sp2 hybridization. 2 sp2 hybrid orbitals of each carbon atom overlaps with each of the 1s orbitals of 2 hydrogen atoms to form 2 sigma bonds respectively. The remaining sp2 hybrid orbital of a carbon atom overlaps coaxially with a similar sp2 hybrid orbital of the other carbon atom to form a strong carbon-carbon sigma bond by sp2-sp2 overlap. The unhybridized or pure 2pz orbitals of both the carbon atoms overlap laterally to form a weak carbon-carbon pi bond by pp overlap. Pi bond doesn't account for the shape of the molecule. All the 6 atoms forming the sigma bonds lie in one plane, and the pi bond lies perpendicular to the plane. Thus, the shape of the molecule is trigonal planar. Hybridization influences bond length and bond strength in organic compounds, which means that these parameters do influence the shapes of molecules. Among sp3, sp2 and sp, in an sp hybrid orbital, the s character is maximum, that is, 50%. Greater is the s character, closer is the orbital to the nucleus, and hence higher is the electronegativity of that carbon. Also, these effects result in shorter hybrid orbital, shorter bond length and greater bond strength of the bonds formed by sp hybrid orbital. In sp2 hybrid orbital, the s character is 33.3%, and in sp3 hybrid orbital, the s character is only 25%. Hence, the bond length is more in case of the bonds formed by sp3 than sp2 hybrid orbitals, and least in case of the bonds formed by sp hybrid orbitals. In sp2 hybrid orbitals, the s character lies between sp3 and sp hybrid orbitals. Hence, its bond strength and bond length is intermediate between them. Let's compare the CH bond lengths and the bond strengths in ethane, ethylene and acetylene. Thus, bond strength of sp hybrid orbital is greater than sp2 followed by sp3 as shown here. And the bond length of sp3 hybrid orbital is greater than sp2 followed by sp as shown here. Thus, the greater the s character, the greater is the electronegativity. Sp is more electronegative, followed by sp2 and sp3. Now, let's look at certain characteristic features of a pi bond. The bonds formed by lateral overlapping of pure p orbitals are known as pi bonds. Let's look at the pi bonds in ethylene. Here, the pure p orbitals of both the carbon atoms, which are mutually parallel to each other, form a pi bond that is perpendicular to the plane of the molecule. Rotation of C around the double bond is strongly restricted, as the pi bonds prevent the free rotation around the carbon-carbon bond. In a pi bond, the electron charge cloud is present above and below the plane of the bonding atoms. Hence, these electrons are more exposed and susceptible to attack by electron-seeking reagents. In general, pi bonds provide the most reactive centers in unsaturated molecules. The pi electrons are more tightly held by the carbon atoms in acetylene, as the carbon atoms are sp hybridized compared to the pi electrons of ethylene, in which the carbon atoms are sp2 hybridized. Hence, acetylene is less reactive than ethylene.